Okay, the next speaker is Professor Alhajji from Calgary, University of Canada. Professor Alhajji is working on big data and social network. His main specialty is big data and social network. His talk title is Facilitating Big Data Analysis Using Limited Computing Resources.
We can go full screen. Yeah. Wait, let me see. View full screen. Where's the full screen? Okay, good.
Oh, thank you.
Yeah. Okay, thank you for inviting me, and I hope you will get yeah, it's okay, I guess it's like this. Yeah, thank you for inviting me to give this talk, and I hope you will benefit from what I will talk about. We are trying to develop some techniques that work with limited resources. We are working closely with the industry in Canada, in Calgary, and our customers, some of them have sensitive data. They don't want to share the data outside. They don't want to go for large computing resources, so we try to develop some algorithms that work with limited computing resources. So I will describe briefly what we are doing, and then I will describe some of the techniques that we have developed for some of our customers, and I will give some results. In the research community, I'm involved in many initiatives. I started this ACM conference in 2008, and it's the top conference in social network analysis. It is classified as a conference. The submission deadline has passed, but still we accept submissions for the symposiums that are collocated with the ASUNAM, the HI-BI-BI, the FOSINT, Open Source Intelligence, and the FAB for the Big Data Analytics. We have the IRI conference that we started in 2002 or 3, and it is running in the US every year in different cities. This year in San Diego in August, we are still accepting submissions if you are interested. I am co-editor of the Encyclopedia on Social Network and Mining. This is classified as one of the best performing encyclopedias developed by Springer, and I am co-editor-in-chief of the lecture notes series on social networks. I am founding editor of 2 journals with Springer. Social Network and Mining is doing very well, and we have Bioinformatics and Health Informatics journal. We run summer school every year in different countries. This year we have it in Turkey in the fall 2017. We teach students and participants different concepts in social network and mining. So we deal with different aspects of data, from data collection to integration to processing, and we do this for different applications in bioinformatics, health informatics, security, web analysis, financial domains. We have a close collaboration with the industry. We deal with Royal Bank of Canada, which is the largest bank in Canada. We deal with many small businesses in Calgary. We deal with the intelligence service in Canada to analyze their data for criminology and term network analysis. We have developed a number of tools because we are dealing with the industry. We try to do proof of concept. We develop a tool. We advance the tool in different versions, and the tools are used by our customers and by our students. So, given any data, in the past, they were using data manually, then they started to store the data in the computer. People were happy that they were storing the data in the computer, fast processing of the data, retrieving only what is explicitly present in the database. So, database were only repositories for the data. They were not retrieving anything beyond what is explicitly stored in the data. Then people started to realize that databases are including gold mines that we can mine, and we can process the data to get some implicit information from the data. So we are not getting information which is not in the data. It is between the difference between explicitly present information and implicitly present information in the database. So all the techniques that have been developed recently after 1993, when Rakesh Agrawal developed his famous a priori algorithm for data mining, are concentrating on implicit information that is present in the data, and big data analysis is concentrating on implicit information retrieval from the data. So we are using network analysis and data mining techniques in our research because network analysis is a very powerful technique. It has basis in graph theory, where you can represent your data using a network where you have nodes and links. Whatever you decide to be the nodes or the links will give you the semantics of the network, and you can analyze the network to retrieve and extract some implicit information from the network. And then we use different data mining techniques in order to link different portions of the data to implicitly extract what is in the data, and we combine both of them together in order to get a more powerful model. To give you an idea of the techniques we are using, a priori was the first frequent pattern mining techniques developed by Agrawal in 1993 at IBM Research Center. So it is a very simple idea, but it had started the revolution in data mining, and people started to get interested in data mining, developed some other techniques which are more efficient and more attractive than a priori, but this was the first technique. It's very simple. Given any data set, you have transactions. It is a relationship between two different entities, the transactions and the items in the market. So the basic idea behind the work of Agrawal is how to arrange the items in the market so that when you go on the market, you can find whatever you want in short time. And you can link different items together to see what items are mostly bought together by customers. You can plan your shelving of the items. You can plan your promotions. So it has very good benefits. So given the transactions as rows and the items as columns, then you can find what are items that are frequently existing together in the same transactions. So first we find the frequency of each single item, then we keep only frequent items that satisfy our threshold, then we get the pairs of items, we find the frequency, we have to access the database and process the database in order to find the frequency each time we get a larger item set. So this was not very efficient because of that. Later on, people worked on some other more efficient techniques for finding frequent item sets. So by processing the data, we can find items that are mostly processed together. So this was developed for the market analysis, but it is a general model that applies everywhere where you have a relationship between two sets of entities. Let's say if we have the web pages and users who access the web pages, you can find users who access mostly the same web pages. If you have samples and you have genes expressed in each sample, you can find the sets of genes that are mostly expressed together in the same sets of samples, and so on and so forth. So clustering is another data mining technique which is very attractive. You try to put similar objects in the same cluster. There are different clustering techniques. Some of them force each object in one of the existing clusters, so you can get clusters that are not very homogeneous, that are containing objects that are not very similar, like on the left-hand side, but some other clustering techniques, they find compact clusters and they leave out outliers that don't belong to any cluster. So you have to decide what is the similarity function you will have, what the characteristics of the objects you will use in order to run this and find good clusters. Classification is different than clustering, though both of them are learning from the data. In the clustering, you don't know what clusters you have, but in classification, you know your classes, and you try to fit your data in a model that will classify the data in one of the classes that you will have. So here we know that we have to decide whether to play outside or not, so we try to find a model that will tell us based on the other characteristics whether we can play outside or not, so we have to develop this model based on the other characteristics. Network analysis, as I said, is a very efficient and attractive model. If we build a network from our data, let's say we have the nodes as the genes and the links between them as there's a link between two genes. If they are co-expressed in the same sample, then we can find what are the communities of genes that are co-expressed in the same samples, what are the most influential genes based on certain measures. We can find the betweenness centrality, let's say the junction like the blue dot there, then the blue node is a very important node, because if you remove the blue node, then you get disconnected components of the graph. So we try to find these important nodes that have high degree, that are junctions, that are close to every other node in the network, and so on and so forth. All these parameters will allow us to analyze the network more efficient and get more information out of the network. So we looked at the literature on data mining, and we found that there are some flaws in the literature, that most of the techniques, they assume unlimited amount of memory available. So they run their technique in main memory, and mostly data don't fit in the main memory. So we must think of scalability. If we want to develop new technique, we should scale beyond the memory size, because we have large volume of data available that may not fit all in the memory. And the other dimension is that we have dynamic data. We don't have static data. So most of the techniques that exist in the literature work on static data. If you change the data, you have to run the technique from scratch, which is very time consuming. So we try to handle these two characteristics, which are very important characteristics when we think of big data, because volume is very important when we talk about big data, and velocity is very important, which is dynamic flow of the data. Data always changes. If you look at variety and veracity, they are common characteristics of all kinds of data, whether small or large. You cannot avoid having integrity of the data maintained. You cannot avoid having different sources combined together, whether small data or large data, but you have to concentrate on velocity and volume of the data. So to deal with dynamic data, we expanded the FB tree construction process. FB frequent pattern tree is the technique that was developed by GMP at Simon Fraser University as his PhD thesis under Johan. So the basic idea is to limit the accesses to the disk to only 2 accesses. In a priori, you have to access the disk every time you go and produce a larger size item set. Now, with this, you access the disk only 2 times, which is very attractive. The basic idea is that you access the disk the first time to find the frequency of each singleton item, and then sort the items based on their frequency. Then the second time you access the disk to read the items, sort each item by the read the transactions from the disk, sort each transaction based on the frequency of the items, and then construct your tree based on that. So this way you build a compact tree structure that summarizes all your data. So using the tree structure, you can inspire the data back. What we did is we realized that this will not work if we have dynamic data. This is good for static data. If the data does not change, if the data changes, then we have to build the tree from scratch. We developed 3 operations that will work on the tree in order to absorb and accommodate new data into the data structure that we have. Now, if we go back to the tree, you will find that the frequency decreases as we go down the tree. Items that are close to the root have higher frequency than items that are away from the root. So you cannot find an item that is deep down in the tree that has higher frequency than an item that's up in the tree. So if we are going to adjust the tree based on new data, then we should be able to swap items, because as the database gets updates, N might get a higher frequency than P. So we have to swap them. We have to pull N up and push P down. The second operation is that if P has other children than N, then we have to split P so that we can swap only N with the part of B that is the parent of N. We don't want to swap without the split. We have to split because P is shared by N and other children, so we have to get the portion of N from the P, and then we swap with that portion alone. The other operation, after we swap and pull and push, we might get 2 siblings that are holding the same item, so we have to merge those 2 nodes so that we keep the tree compact. So given this structure that we got out of our database, then we get some updates on the database. We have 2 choices. Either we go and develop the structure from the beginning, from scratch, or we can incrementally update the structure. For large data sets, developing from scratch is not affordable, is not possible. So we go for incremental update. So if we integrate the additional new part of the database with the original database, we find out that M will get the highest frequency. It should be on the top of the list. It should be the closest to the root of the tree. So if we look at the tree, we find M deep in the tree, so we have to pull M up. So we find that A has frequency 3, M has frequency 2, so we have to split first. And then, after we split, we exchange M and A. Then we split F, we exchange M and F. Now we have another M down there. We have to go and pull that up. So we get this exchanged only. We pull it up, we get, F has 2 children, so we have to split F first, and then we swap. Then we get 2M occurrences under the root, then we combine them, then we continue combining until we get all of the tree compact. Then we start to add the new transactions in the tree structure, and we get the new tree without from scratch computation. So this way we can handle dynamic databases, but handling dynamic databases is not enough. We need to handle data sets that grow beyond the main memory without using supercomputing or without using external devices. So what we did, we re-implemented parts of the operating system to accommodate our technique, and we added one more step to our algorithm, because in the original algorithm, what they did is that they sorted each transaction alone based on the frequency of the items. Now, in addition to sorting each transaction, we sort all the transactions together so that the transactions that have the most frequent items in the beginning comes on the top of the list. This way we build the tree structure left to right, top down. So when we grow out of memory, when we need more memory to store the new links, the new nodes, then we can throw on the disk the left-hand side, because no more transactions will come that will be added on the left side. So always we need to keep the right side of the tree, and the tree grows on the right side. So now our upper bound is the available disk space. We don't care about the memory. So for this, we had to re-implement some parts of the operating system, and we developed our virtual operating system on top of the existing operating system so that we can handle all these processes, and we can build tree structure for large data sets. So we tested this using different data sets. So if we have 250 megabytes of memory, if we have a small data, then we can manage. But as the data set size grows, then we may go out of memory easily. On the right-hand side, you see we go out of memory. We cannot process the data. But with our technique, while the normal FB growth that was developed by Agrawal and his student will not work after certain data size, our technique works because the upper limit is the disk space that's available in your computer. So we tested this on huge data sets with very limited main memory, and we could process data as long as we have enough disk space. So we developed some other techniques for intelligence services, because mostly they were using manual processes in the past to analyze criminal networks. But criminal networks have different characteristics that are very challenging for investigators. These criminals are so clever that they try to hide. They don't communicate openly, they try to hide, so data is incomplete. And data may not be correct. They may try to trick the investigators. You have to get data from different sources, transform data, combine the data together. We have the fuzzy boundary problem, that is, investigator cannot judge whether a certain person is a criminal or not. How to judge this? You have to have a more comprehensive study of existing data. And the network is very dynamic. People leave the network, join the network, so you have to have very effective technique in order to handle the data. So as I said, traditionally they were manually analyzing documents, intelligent investigators, and derive the network. This is not practical. Then they started to develop some automated techniques that visualize the network and allow for effective analysis. What we did is we did a tool that we developed our own tool that allows investigators to look in the past for detecting the reasons for an event that already to be investigated, already happened and is to be investigated. We try to find out what were the reasons for that so that we can avoid them in the future. And we also can investigate and predict future events so that we can avoid them. So we can detect and resolve, and we can avoid future events using our technique. So we built a tool called NetDriller that allows you to collect data and process the data using different social network analysis and mining techniques. So the core part of NetDriller is NetBuilder. You ask the NetBuilder to connect to different sources, and it collects data from different sources, including traditional and social media, and you collect the data, you build the network from the data, you analyze the data, and then you find out what are the important key persons in the data that you have. So you can set what are the key terms that you want to use in your analysis so that the NetBuilder will use those key terms in building the network. You can give a weight for each key term. You can also decide on certain individuals to be investigated and to be in the core. For example, if you say, I want to start with bin Laden as my core, then you can find who are other persons that are connected to bin Laden. You build your network incrementally based on who has been added to the network. Then you can set who are the key individuals that you start with, and you may decide on certain range, time frame during which you want to do the investigation. So during the last month, who were very active criminals in certain area, in certain context or certain framework. So, and you decide on what are the sources that you will use in your investigation, either internal or external sources. And the NetBuilder will connect to the sources, extract the information, build the network, and then you can analyze the network. You can find key persons in the network and try to study how the network will restructure after you remove these key persons. We tested on 9/11 network. We find the key persons at the first level. We removed them. We checked how the network would have restructured after removing the first level, second level, third level, fourth level, fifth level, sixth level, and we found out that it was well planned, that it was very hard to dissolve the network by removing more individuals, more persons from the network. But we studied the Madrid attack network. It was not well planned. After removing the second level important key persons from the network, we found out that the network started to dissolve, and it was easy to get rid of the network by removing certain persons from the network. We applied the same thing to study gene expression data analysis. We studied different types of cancer. So far we have studied breast cancer and prostate cancer. We tried to analyze documents, the papers that have been written related to a certain type of cancer. Let's say here, prostate cancer. We analyzed the PubMed literature on prostate cancer to find what are the genes that and the proteins that have been mentioned as related to prostate cancer in those papers. And we built the network, and we try to find what are the key genes. We try to derive the most important genes mentioned by different publishers, and we give weight to the publisher based on the H index of the publisher and the citations of the publisher and who other authors have cited and the importance of the other authors. So we have a very complicated formula to find the importance of every publication so that we don't give same weight to every gene or protein that we derive. So we find what are the diseases that are related to each set of genes that we derived, and we find the network of the different molecules, and we find the communities that are related to prostate cancer, different communities of molecules, and then we find what are the diseases that are related to each one of these sets of genes forming each community. So all of them are related to cancer, but some of them are related to other diseases. So it is not each disease is isolated from others. So diseases are interrelated, and we find out that some genes are related to more than one disease. So we applied the same thing to financial domain. We collected tweets related to RBC because RBC had some advertisement and they wanted people to move their mortgage to RBC, and they want to find out what is the reaction in the community for what they have advertised. So we collected all the tweets during a certain period of time related to RBC and that advertisement, and we find during 20 days how the tweets were reacting to the advertisement and what are the key terms in each tweet, and we find the communities of customers of RBC and what they are discussing and how they are reacting, and we found out that certain piece of information, certain key terms are not well realized and were received by the customers of RBC. Then they have to re-advertise, and we analyzed the same reaction after the advertisement, and we found that the reaction has changed based on highlighting that key term. So we developed other tools and techniques. We developed an interface for databases. If you look at traditional databases, every database contains crisp data, and every user can run the same queries, get the same result. In the 80s and 90s, there was huge interest in fuzzy databases. And they tried to integrate fuzziness in databases so that everyone can query the database and return what he or she understands and what he or she targets. For example, my understanding of good student may be a student over 70. Your understanding good student may be a student over 80. So if you query from the database a good student, then you should get different result than what I get. So they failed because they tried different techniques and different approaches, and they were not accepted by the commercial database industry. We tried a different approach. Instead of forcing the fuzziness in the database or forcing the fuzziness in the query side only, we developed an intermediate layer that absorbs the understanding of every user or every group of users, so that every user will declare what he or she understands of different fuzzy terms, and the tool that we developed will map the data based on your understanding at query computation time. When you run your query, you get your result, I get my result, my interface is the same as your interface, but the intermediate layer has absorbed your understanding, has absorbed my understanding, and we get, everyone is satisfied because everyone gets his own result. So this can connect to different data sources. We developed another tool that helps newcomers to Canada to decide where they want to live, because Statistics Canada opened existing data to the researchers to benefit from that data. So they run a competition who could use the data the best. We developed this and we ranked in the top 15 applications out of thousands of applications that were developed to use the data that was made public by Statistics Canada. So this, depending on different parameters and different characteristics, helps you to decide which city, which community would fit you best as newcomer to Canada so that you can adapt and you can integrate in the society better. So we developed another tool that helps people in shopping based on whether you want to save on gas or on time or on spendings or on the three of them. So it finds you the best route to the market, the closest market, the best combined cost, because you might have an item on sale at market X, but if you go to market X, you may purchase some other items and your total bill will be huge. So instead of being tricked by market X, our tool will get you the total amount that you will pay and try to optimize total amount that you have to pay based on your target, what you want to shop for and what you want to purchase. We have developed that tool using our techniques for predicting stock market prices based on different sources. And we have also developed a technique using Statistics Canada data to compare your health indicators to health indicators that are commonly acceptable for persons of your characteristics. And it highlights what you have to care for in order to keep fit. And based on this, we developed SANO as a tool that that helps you to train and keep your body fit. So it indicates that you have to train your neck, your shoulder, your foot, you have to walk, you have to make certain types of sports. So it will warn you and it will always display your health indicators. So to conclude, we have utilized different data mining and network analysis techniques in order to build different tools that help our customers to run their businesses. We have customers in health informatics, bioinformatics, security intelligence, web analysis. We help some customers to optimize and customize their websites. So we have shown how these data mining and network techniques can be helpful in practice for different types of industry. So this is the end of my talk, and I will be happy to take questions.
Alhaji for his very useful talk. May I ask for any question or comment? Okay. That lady.
Okay, thank you. Is there a question?
Thank you very much. As you experienced in social network analysis, I have two questions about social network analysis. First of all, which kind of data mining algorithms, such as associated rules, pattern mining, or clustering, are useful for forecasting or predicting new events? I mean event prediction or event detection and tracking. And the second question is, in the case of social network analysis and graph mining, are graph databases such as Neo4j, TimeTime, OregonDB, etc. useful for storing data, or maybe we can use traditional NoSQL databases? Thank you.
Okay, Thank you. So for the first question, for prediction, it depends on your data. Sometimes you may represent your data as a time series. We have another technique that we developed to analyze large time series to predict stock market prices, let's say. So you have to find the trend and see where the trend is going, what are the external factors affecting the trend, and try to predict based on those. It depends on the data, if it is time series data. If you have transactional data, then free computer mining will be better because you try to find what are items that are frequently existing together, whether they are genes, whether they are customers, whether they are web pages, and you can predict based on your discoveries how these will be in the future. So it depends on your data, how the data is structured. And for storing your data, those new databases are better to store the network than traditional database, because if you store the database in a graph database, then the network will be more natural to store. But if you store in a traditional database, still you can store, but you have to handle the mapping between the network and the traditional database and back. So there might be a semantic gap between what you store and what you get back, like as if they were storing XML in databases. So they were storing XML as relational database, and they were always talking about the semantic gap between relational database and XML until they developed the native XML databases. So the graph databases are better to store network.
Okay, thank you. Any other question? Okay, Dr. Alhajj, you have a good knowledge in both theoretical and practical side. So do you have any publication on your extension to FP growth algorithm?
Yes, we have 2 journal papers and couple conferences. I can share them with you.
Published recently? Or?
Yes, some of them published recently. We have been publishing on this for the last 10 years, so I will share them with you.
Because it's my field of teach to student. Okay, I will introduce you quickly. Okay, thank you very much, and please admire Professor Alhajj.
Thank you.